I'm going to be talking about thread local storage, so a very small corner of the C specification, not used very widely except when it's extremely useful. So really into the weeds here. So some disclaimers before we get started. There will be assembly, kept to a minimum, and I'll try and explain it, but fair warning, there'll be a lot of pointers, right? We're at a CHERI conference, so pointers are the name of the game anyway, and things like language runtimes particularly like pointers. And there'll be lots of diagrams of pointers. So if you ever done computer science course and had little boxes with arrows, well, I'm afraid that's going to come back for today. And I've only got 15 minutes. I could go on for a lot longer, so I'm going to be omitting a lot of the actual nitty-gritty details and just trying to give a much more visual overview of what's actually going on. I can talk a lot more afterwards if you're somehow still interested. So some background. What is this TLS thing? So historically, it was this extension that both GNU compilers and Microsoft compilers implemented. And then for C11, C++11, this got standardized as part of the language. So what does this look like? You declare a variable x here, but we add this thread local keyword onto it. And then we write our function here, and it accesses x. It looks just like any other variable access. Looks like it's accessing a global. But something slightly weird happens if we start running this code. So if we have thread 1 running, it's going to increment x and give us back 1. Run it again, it will give us 2. Again, it will give us 3. But then thread 2 comes along, runs our function, and it sees a separate copy of this variable x. And so it gets back 1, and then 2, and then thread 1 comes back along and it gets back 4. So somehow these two different threads have a very different view of this world, even though there's just this one variable declared here in the source code. So in the model, right, we have some number of threads here. This can be very dynamic things, they come and go. And each thread, whenever it takes some reference to our value x, whether explicitly or perhaps just implicitly, like in our previous example where we just modified x directly, we see a different copy of this x. So how does this work? So slightly more complicated example, let's say we have two libraries here. We've got two sets of variables, x, y, z, and a, b, c. Well, library 1 has a little bit of data that it needs for its variables, and library 2 has a little bit of data that it needs. And so at runtime, we sum all of this up, allocate a big block of memory, stitch it all together, and that's where all the variables live for that particular thread. And as threads come and go, we will allocate new copies of this memory from scratch. But then how do we get to this memory? Because it's all very good living there, but I didn't write, thread.x, I just wrote x. So we reserve a register in our architecture, typically referred to abstractly as the thread pointer, and it points at this block of memory, and so the runtime maintains this, and each thread will have a different value in that dedicated reserve register. So then say we want to access variable b, well, how do we get to b? Well, we take what the pointer is in our thread pointer, and we add on whatever the offset is to this variable b in this block of memory. And an important observation here is that every single thread will have the same layout for its block of memory, right? All these allocations are just the same template multiple times. So this offset here is a constant throughout the lifetime of the program, no matter what thread you're in. You just need this thread pointer to decide which bit of memory you're accessing. So then the question comes, where do these offsets come from, right? We've just turned one problem into another. So in the simple case, we have just an executable. And in that world, when we load up our program, the very first thing that gets loaded up is that executable itself. And then it goes off and it loads off all the other libraries that it needs. But if the executable is always first, then that means that its offsets are always the first ones. There's nothing before it. So actually, when we link our executable, we know that the thread pointer is going to be pointing directly at the block of memory for that. And so we can just hard code those offsets in based on what we decide that layout of memory should be for the executable. And so first little bit of scary assembly. This is what it looks like on ARM for our next function from the previous slide. So here is our thread pointer. Here is split across two instructions because of risk encodings and things. Basically the offset 16 being added onto our thread pointer. And then finally here we can do our load, add, and store. But all we've got here is just hard-coded constants in the actual executable that we're running. But in the general case, we're not able to hard code this at link time, right? Maybe this variable doesn't actually live in the executable, it lives off in some other library. We have no idea where that's going to be. Or we're a library, we don't even know where we're going to be loaded, what's coming before us. So we need some amount of support for dynamism in the more general case. So this offset is a variable. Where is this variable coming from? Well, we already have this convenient data structure called the GOT, which is where we get our pointers from. And the GOT is this data structure that the runtime linker is going to fill in addresses with when you load up programs, when you load up libraries. And so we can just reuse that machinery, but instead of storing pointers, we're going to store offsets. On non-CHERI, they're basically the same thing. On CHERI, one's double the size of the other. But the data structure is basically the same. So the runtime loader is filling this in for us, but then we have to go and find it. So how does that look? Well, we still have our thread pointer here, but the assembly's changed a little bit. So the first thing that we're doing here now is we're doing this load into x8, and this x8 is going to hold our offset. And so now, because we're loading from memory, that can be a runtime variable value. And so here, right, rather than loading from our thread pointer plus some constant, we've now got a variable offset for our load instructions here in order to be able to make that offset be dynamic. There's another little wrinkle in that POSIX has this thing called DLOpen, which makes everyone very unhappy the moment they discover it. And DLOpen says, you thought you knew what libraries I needed, actually I'd like you to go load another one please, but you've already started running the program at that point. So it's a function, you give it a string that is the library you like it to load, it goes and finds it and it loads it. But what if those things define new thread local variables? We've already decided at load time how big that allocation is going to be. We can't just grow it because there's probably not space. We can't move it elsewhere because we may have already taken pointers to it. We could do it for new threads, but for the existing threads we have a bit of a problem. So how do we solve this one? Well, in a sense we don't, right? We take the view that we can't move this allocation, so we're going to have to allocate memory elsewhere. But then how are we going to get to that memory? Because our thread pointer is just pointing at that block of memory. So firstly, we don't inline a whole bunch of code to do this. We bail out and just decide to call a magic runtime function. Sorry, it's going to be a bit slower. Don't do this if you want your code to go faster. And then the runtime linker can reserve a little bit of extra space in that allocation that we made to track its own data structures in order to keep track of where these extra little allocations are. So going back to our picture, we have a thread pointer pointing at this allocation, but I lied to you a little bit. All right, so we have this extra bit for library 3, and we reserve some space on the front. This points at this thing we call the dynamic thread vector, and then it has an entry for every single library that's loaded, pointing at where the start of its block of memory is. So for these libraries 1 and 2, it's straightforward, it just points right back at the initial allocation. Technically, maybe you don't need those, but they're there for convenience rather than having to special case them. But library 3 now points off at this separate allocation. And so if we come in and say we'd like variable j, then the runtime linker can follow this pointer here for us, go along to library 3, and then say, oh, I know j is over in this allocation instead for us. So that's TLS as it exists pre-CHERI. What happens when CHERI comes into the mix? Well, in initial implementation, not a lot really. We took this same model, and everywhere there was a pointer, we just turned it to be a capability, and that was kind of it. But this has some problems. So we have this one big memory allocation. That means that the bounds for that thread pointer is that entire allocation. That makes us a bit sad from a CHERI perspective. So if we want to restrict those bounds, we have to insert extra code to do so dynamically at runtime. Every time you're doing that pointer arithmetic, you have to find the size of that variable, restrict it down. This gets a bit inefficient. It also doesn't give us great warm fuzzy feelings about the security of this story. But maybe it's just about okay. And those DTV entries as well, they behave a bit like TP, right? They're pointing into big blocks of memory. Okay, this time they're the block of memory that just that library is using, but there are still a whole bunch of variables there potentially. So we still would want to be able to restrict that down. And then how on earth does this even work with compartmentalization, right? Compartmentalization is based on restricting capabilities, and we have the one capability that gets you to everything. You're either a compartment that does TLS or doesn't do TLS, nothing in between. So this is a bit sad. So how do we solve this problem? Well, Computer science has a great trick. It's called indirection. And this solves many problems, including this one. So if we introduce this extra level of indirection with this data structure that's dubbed the T-GOT, so we had the GOT for our globals, so now we have the T-GOT for our TLS globals, and then we can store a table not of just the data, but a table of the pointers to get to all our different variables. And so TP, instead of pointing directly at the data, now points at our table of pointers. So if we want to, say, get to variable y, we can come along here, load this capability, and this capability in the table is only going to have bounds of y. So we no longer need to have any dynamic derivation of bounds in our code. So how does that look in the assembly world? Well, on the left we have our constant offset case. So this offset here, whether we know what this offset in the T-GOT now is, whether it's a constant or not. So we still have a constant here, this time it's 32 rather than 16. But instead of just doing an add of TP, we've now done a load from that offset, and that's given us a capability to the variable x. And then down here we have the same load increment store as we had before. In the variable offset case, basically the same transformation again, right? We have to go to our GOT to find out our load offset, and then we apply that offset as a variable to get to our capability and load from that to get the bounded capability. And so we can sort of atom smash these two together and get a working model. And then for DL open, essentially we add more indirection there as well, right? So that dynamic thread vector, instead of pointing directly at our data, now points to tables of pointers as well. So everything can now get bounds. There's still a magic function called, and actually with the generated code it mostly looks the same because it's all abstracted, but there's more pointer chasing going on behind the scenes. So I kind of had to do the next slide, and I apologize in advance, but here's how that looks when you compose it all together. A little bit of a spaghetti mess of arrows, but if you start to follow things around, then things make sense, right? So you want to get library 1's view of y, you follow your thread pointer into the T-GOT, you come along to your offset for y, and oh look, you have the pointer to y. You want to get to library 3's data, well, you have to go through the DTV because we said that one was dynamically loaded. Then you can come along to library 3, oh look, you've got to library 3's T-GOT, and now over here you have a pointer, say, to I, or maybe a pointer back into C because it decided to reference library 2's data, even though it was dynamically loaded. So a little bit of a tangled mess, but somewhat decipherable if you stare at it a little bit. So a moment of calm. Apparently blue is a calming color, so that was convenient for the slides. What about compartmentalization though, right? I was just talking a lot about spatial safety. So we had this model where we're pointing at this big block of data. Compartmentalizing it was awkward because we had a single pointer. We now have indirection. Great, we now have a bunch of pointers, but we still have this one pointer hanging off of TP. So how can we still compartmentalize this view? Well, the beauty of this is that we can just, well, first of all, if we want to hide things, we can just make the pointers not exist. But how do we then deal with the fact that we might then call into library 2, which needs to have this pointer and not have these? We could go dynamically rewriting that table all the time, but that's probably going to get quite inefficient. But we can just duplicate this and context switch TP around. So we can have library 1's version of the T-GOT, and we can have library 2's version of the T-GOT, but because they point at the same data ultimately, that all works out fine. That extra level of indirection saved us. And then once we're done with library 2, context switching back to library 1, we just flip that TP register back. So this is not yet implemented. This is our sketch of what we're going to do. Everything up to this point has so far been implemented. So future work, as I say, implement this compartmentalization model. We think it will work, but we haven't actually done it, so there's probably something we've missed. Performance of this. We don't expect it to be significant overhead, but it will be some overhead for some workloads. In particular, TLS often gets used in malloc implementations, and we don't want to slow that down too much. So hopefully we can make sure that that still remains reasonable performance. And yes, we'd like to ship this out to everyone in a future release, and we'll try and do so in a responsible way that will not break your system when you update, which is also a hairy problem in and of itself. And with that, that was everything. Thank you.